Hello and welcome to our vodcast for Math 130. We'll be discussing exponential growth and decay. Exponential functions are functions involving exponents in which the variables are raised to the power. They are predictable and consistent. You might be familiar with some common uses of exponents such as squared or cubed values. Here, we can see that a squared value has been used in the common expression of Pythagoras' theorem. In this case, 2 is the exponent. Furthermore, in the area of a circle, we can see that the exponent is again 2 for a squared value. An exponential function with the base a is denoted by fx to the a to the x. Notice here that the x is the exponent. As such, these graphs are not simple straight lines. However, the variables of x and y are still intrinsically linked and the graphs increase or decrease accordingly. Exponential functions are used in a variety of applications in the real world, including for financial models, for interests on loans and funds. It's also used to calculate depreciation values on a variety of things such as cars, tools, or property, which is extremely useful in tax purposes. In science, exponential functions are used in a variety of purposes, including in population growth, pH, radioactivity, decay, heat loss, tissue decay, and growth. It is used to help analyze experimental data to determine the rate of decay or growth process and make predictions based on the data. Exponentials with a positive value trend upwards. This is considered to be a positive function. It's like a smiley face. It's easy to remember because happiness is positive. As y increases, so does x. Also known as growth, it's often used to describe the relationship of bacterial growths, stock growths, population trends, and so forth. As you can see, as the x value increases, the y value gets larger. Exponential values that are negative, where x increases, we can see that the y values decrease. So as x gets larger, the y's are getting smaller. This is known as a negative function, also known as decay. This is used for financial services in the depreciation values of various things, such as cars and tools. Decay rates of various substances, such as radioactive decay. Any quantity that increases or decreases by a fixed amount at regular intervals is said to possess exponential growth or exponential decay. At the algebraic level, there are two equations that are used to illustrate the concepts of growth and decay in applied situations, or exponential decay. Algebraically speaking, I've totally screwed this up. One thing that is important to keep in mind when discussing exponentials is the relationship between exponentials and logarithms. Logarithms are another way of thinking about exponentials as they are intrinsically linked. For example, the exponential y to the x can also be considered to be written log yw to the x. For example, 2 to the power of 4 is equal to 16. Alternatively, that can be written as log 2 to 16 equals 4. That means to what power is 2 raised to equal 16? Both equations describe the same relationship between 2, 4, and 16. The difference is that while exponential forms isolate the power, the log form isolates the exponent. Here is an example of growth and decay. Mary wants to buy a new car that costs $15,000. She currently has $10,000 in a savings account that increases by 12% per annum. How long will it take Mary to reach $15,000? Here we will employ the formula for growth. Using the amount of money of the car for Y, Mary's starting bank balance for A, and the rate of annual growth, which is 1 plus the percentage amount, which we have turned into a decimal for the purposes of this. And what we need to find is the exponential x, which is time. We know that the opposite function of an exponential is a logarithm. Thus, to find time, we need to take the log of our arithmetic values. So using our figures, we get log to the 11,200 of 15,000. Using our figures, we cannot use this on a calculator, so we're going to use the change of base formula, whereby we put the log power to the numerical value of log 10 and divide, which will result in this. This we can now easily put into the calculator, and we can find an approximate time of 1.4 years. So it has taken Mary approximately 1.4 years to reach her goal of $15,000 for the new car. During this time, the car's value has now depreciated at a rate of 15% per annum. We now need to find out how much the car will cost and how much money Mary has saved. To work out the new cost of the vehicle, first we must work out the value of the depreciation. This time we will use the decay formula. Now we know that the time is 1.4 and we need to find the Y value, and the depreciation rate has also changed. So for 1.4 years of an initial value starting at $15,000 at a rate of decay of 15%, we can easily use a calculator to find this out, leaving us with a new value of $11,947. To find out how much money Mary has saved, now we need to work out the depreciation amount. We need to subtract the new amount from the original amount, which will leave us with a saving of $3,053. So during the time of 1.4 years that it has taken Mary to save her goal of $15,000, the car has depreciated by $3,053, which will total the amount that Mary has saved during that time. The important things to remember from this vodcast are that exponential functions are when the variable x is the exponent. Logs are another form of writing exponentials. You also need to remember the formulas for growth and decay, and that growth is a positive function and decay is a negative function. This has been an introduction to exponential growth and decay. We hope you have enjoyed listening to this and have found it informative.